Yeah, so thanks for coming, and obviously Moov for organizing this whole beautiful concept of a developer conference in fintech, which is, I guess, not so common, but hopefully will grow bigger and bigger year by year. And yeah, this is really exciting. So, and the topic I'll present today is large language models, right? Obviously, everyone has heard of those, and in particular apply to financial data, right? So yeah, it's a bit about me. So I'm the CTO at Entropy, also one of the founders, and yeah, some links. And so what we do at Entropy, this is kind of like really kind of a summary of our like long-term mission, right? Is to kind of democratize superhuman understanding of financial data, right? Which obviously is a can of worms, right? There's a bunch of parts of this, right? There is parsing, normalization, like categorization, obtaining this data, like that whole stack, right? So our vision is to completely abstract away humans from really having a role in trying to understand this data and instead focusing on products that you can build on top of it. And yeah, so this is effectively kind of, I guess, like a very explain like I'm five illustration of financial data, right? Like ultimately it's just transactions, right? Like this transaction can be, you know, whenever you pay with a credit card, or it can be an invoice, right? Which is kind of an origination, you know, or a request for a transaction. It can be a bill, a receipt, in whatever form, a check, right, you like, but ultimately the financial data we will be talking about is effectively transactions between people and entities, right? And these entities can be like businesses or charities or whatever, right? So it sounds pretty simple ultimately, right? It's just transaction data, right? You have a timestamp, you have an amount, source, destination, and that's it, right? But it's really a treasure, right? Like if you understand this data, right, it's kind of like the payments graph globally, right? Like it kind of represents the transfer of value in the world, right? You can do a lot of cool things, right? Obviously, a lot of us are working on different parts of this, right? But you know, you can do like financial management, like stock market prediction, carbon footprint estimation, you know, underwriting, PFM, BFM, cohort analysis, fraud detection, a lot of different things, right? So this data like kind of looks like this, right? It's effectively, all right, so we have this table, right? We have a transaction ID, you know, currency, amount, all the usual suspects, originator, receiver, location, and everything, right? And that's it. Like, what's really the problem, right? Like, we just take this data and then we, you know, maybe just plug it into some underwriting model or do whatever we want with it, right? Like, show it to our users or yeah. But this is not exactly so easy, right? Unfortunately, there is no single SQL table anywhere in the world which has all the global transactions in it, right? With nicely, clearly formatted fields. And yeah, so before we get to that table, we have to look again at how transactions actually work, right? And there is actually, you know, multiple, this is like a credit card payment flow, right? And there's, you know, there's like different Excel sheets and P&L calculations and receipts and bills and invoices and a lot of bank statements, right? And in like a lot of different forms that this data comes in, right? Of course, not mentioning that this is global, right? This is in different languages, it has different locations, it changes over time. So this is effectively the same picture of that table except the reality. But this is really where we come in, right? So what Entropy does is we allow you to start with the raw stuff, and then we give you the kind of the nicely formatted and usable stuff, right? And everything in the middle, right, from like OCR and categorization and finding like recurrence patterns and account holder analysis, that's what we have tooling for you to be able to access, right? So let's focus on one of these problems, right? Similar to the previous to the focus of the previous talk by Pave, right? Like this is kind of like transaction categorization, right? Like so this is a bank statement on the left, and it has a bunch of transactions, and we want to understand what is the category of every single transaction, right? Or label, or whatever you want to call it. And this is kind of the lay of the land, right? So obviously, it would be great if we could categorize all the, well, I would say unambiguous transactions with 100% accuracy, right? 100%, I guess, is defined, right, that if a human is given, like an hour to look at it, they would all agree that this is the correct category, right? So, but like to get to 100% or even near 100% accuracy, right, there is, of course, a rising cost usually, right? If you want higher accuracy, you usually want to pay more. It's a higher latency, right? Usually it takes a longer time to get to a higher accuracy. And usually larger models do better, right? At reasoning and thinking and kind of weighing up all the pieces that make up a category of a transaction. Yeah, so this is kind of the model size illustration, right? So, and so the question is, all right, so we have kind of established that to get superhuman accuracy, right, which is the vision, we need a very large model. And large models which are processing text is kind of called large language models, right? So let's look at one aspect of these models, right? So we put in some tokens in the input, and then we get some tokens in the output, right? And we can do this then recursively to be able to generate really any kinds of outputs from a model. And kind of, if we want to focus on accuracy, another general kind of rough trend is that if we're using more tokens, if we can afford to use more tokens per transaction, that in general gives us a higher accuracy, right? Like a bigger prompt, or we can also maybe put some examples in the prompt and then maybe, explain everything. And then, if we have more tokens to work with, then our accuracy should go up, right? So let's kind of focus on this tokens per transaction, right? Like how do we kind of maintain the same accuracy but somehow reduce the amount of tokens that we use for every single transaction? All right, zero shot. I guess everyone in this room has tried to do some zero shot predictions, right, using ChatGPT and then maybe like Anthropic's models or something else. And of course, right, you can put a transaction in with some instructions, and then you get some labels. All right, you can sometimes get multiple labels or one label or however you want to put it. Right, so our tokens per transaction here, right, is that we have spent some tokens on the instructions. We have spent some tokens defining our transaction, and then we also have spent some tokens in the output of the model, right? And we're paying really for both, sometimes slightly different, but approximately kind of the same ballpark. So it's the sum of all those three. And right, and so the accuracy of this thing is, so this is on a pretty hard data set, so it's quite below human. It's not exactly, at least in our experiments, something like 30%, like some others have found. So this is the F1 score actually, not really accuracy, but let's say give it a good proxy. But it's still like quite far below human accuracy, right? So, all right. So then, but we want superhuman, right? So okay, so then let's try a few shot, right? So let's try to also put some examples in the prompt and then see if that improves stuff. This is an important part. What we found, if you put just some random examples in the prompt, or maybe just fixed examples in the prompt, then sometimes accuracy improves. Usually it improves, but not by too much. What really does help is to put the right examples in the prompt, right? So from a pool of, let's say, like 100 million transactions, we want to pick 10 which are most helpful to classify this specific transaction. And so the general algorithm we are using is we want to pick examples which are as similar as possible to the transaction in question, but as different as possible from each other. So kind of maximize the mutual information between these examples and the problem we're trying to solve. That's very important. And with this, we can actually get much, much better. So this is as a function of number of examples. Obviously, it flattens out at some point. And there's, of course, technically there should be some error bars in there, but so we're kind of golden, right? We have reached a ballpark of an average human with the right examples. But then our prompt is enormous, right? So with like 20 to 30 examples per transaction, we're spending, tokens on the examples, tokens on the instruction, the transaction itself, and the labels. And it becomes something where we feed in a transaction and we get the results after, just a label for one transaction after 30 seconds, which is not very useful. All right, so then let's try something else. Let's try to run this thing in batch, right? So we keep the same examples, and obviously we need to modify the similarity function here, right? Reality is maybe we want to batch together similar transactions so we can have a similar similarity function in our examples, right? So here in this setup, right, we can kind of divide out, like abstract away the instructions and the examples, right? Because the same thing, which is a static piece of text or kind of a static amount of tokens that applies across all of our examples, right? And so obviously the more transactions we run through using this method, the first term kind of falls away, and then we're actually only spending transactions plus labels amount of tokens, right? So if we want to classify like 1,000 transactions at once using this method, we can accurately do it, but then at the same time, right? Obviously there's other constraints that might come into play, like context length and things like that, but let's assume that that's going to keep increasing, right? So this is actually, so not so fast, right? So context length is hard, even though you can technically feed in a lot of stuff into a model. Actually, the reality is that the more stuff you put into the prompt, at some point it starts to ignore it and it starts to confuse things. And this is also kind of natural, right? Like kind of the data these large language models is trained on, right, which is kind of public text, right? The dependency between tokens in public text is usually, maybe a few words, maybe sometimes 20 words, right? If you give it like some classical writer and their book, it might be a few pages, right? But these models are not used to seeing such long-term dependencies of like 6,000 tokens, right? So actually running them in batch, you're going to be winning tokens, but you're going to be sacrificing accuracy. All right. So last resort, right? Let's actually try to then remove all this stuff from the prompt and just kind of fuse it into weights, right? It's kind of a static piece anyway, right? Like, why cannot we just, update the model with it and say, okay, hey, like for the next, from now on, you're gonna, kind of teach it the prompt. And this is kind of fine tuning, right? For this, we do need to have access to the model or access to like a fine tuning endpoint if anyone's offering that, right? Or anything like this. And so here, right, we have kind of the same token pattern, right, as with the batch, right? We have transactions plus labels per transaction, but then we potentially don't have this huge batch problem with accuracy and stuff like that, right? And this actually does pretty well. Actually, on this specific data set, it outperforms human accuracy. So this is a log scale on the x-axis, the amount of data. So for each point, there's a separate model. So this specific one is a 7 billion 16-bit Llama 2 model, but you can also use other models, right? So, and yes, it takes quite a lot of GPUs, right? And you need infrastructure for this, but it's doable. And you can, so this is after like 25,000 examples. It reaches an F1 of like 93, right? Which is pretty good. Now, the human accuracy here is kind of human accuracy of our internal labeling team, which is obviously going to be lower than our head of finance, right? For sure. But nevertheless. Okay. So, yeah, and this is actually, so this is another, so this is on a different data set, right? We don't have infinite amount of GPUs, right? So this was previously run. This is kind of how the accuracy scales with the number of weights in the model. So this was run for a 7 billion parameter. This is actually on Llama 1, a 13 billion parameter, and a 65 billion parameter model. So the bigger the model we use to fine tune, it seems to, I guess, kind of naturally also improve accuracy. All right, so we kind of, if we zoom out again, right? All right, so we got some trend there, right? We established that, right? Some fine tuning and then larger models. That's cool, but these models are still very large, right? It's like even like kind of the smallest open source foundation models is like 7 billion parameters, right? Multiple tens of layers, and if we want to process, like thousands of transactions per second, right? It is still not exactly doable, right? So the one transaction per second is kind of, if you just want to use the ChatGPT API, the prompt, let's say 0 shot, right? And then so kind of with our fine-tuning experiments and with some batching and some cool prompting, you can get maybe like 10 transactions per second reliably. But how do you get here, right? Like how do you get to like thousands per second, but still somehow keep accuracy maybe, right? So we need a large model, but then the accuracy falls off if we have a smaller model, right? So, all right, so let's look at a different problem to see how we can get further. So let's look at entity recognition, right? And this is a transaction which looks like nothing has been mapped away, but all of this is randomized. So yeah. Let's try to actually like figure out what is the entities in this transaction, right? Like where is the organizations? This is like an ACH transfer, right? Like where is kind of the other bits? And we want to build a flow to try to tag these things. One thing, if we look at this closely, right, is kind of like the structure of these entities is not like if we would have changed the ID number, then the tag on Shopify would change. That's not the case, right? Probably for all transactions with even different IDs. So kind of the fact that the organization is in the beginning is independent of the type of reference number we have at the end, right? Or usually after the INDN, it's either a person name or an org name, independent of the actual name of the org, right? And it kind of, we actually start to see, so maybe actually, some of these entities affect others, but then, some other group is actually independent of the first ones, right? And actually, we can look at different parts of this transaction independently of the rest. So maybe like we don't actually have to feed everything, even one digit in the reference number changed, and we feed it again through this huge language model. So can we think in that direction? All right, so this is kind of, an illustration of this. So if we have our transaction in question, which is the blue one, but we have already kind of classified or analyzed the yellow ones, right, the similar ones. Can we use our results on the yellow ones to try to guess what the blue one would be without, feeding it through, 280 billion parameters? So effectively, if we run the model on the yellow ones, can we actually retrieve the blue one from cache in some way, right? Even though it's not exactly the same as all the other ones. And yeah, it turns out you can, right? So this is a specialized cache specifically for entity recognition in transactions. And so this actually with not so many examples. This is like something like 20 million transactions. You can get a hit rate of something like 95% on cache. And this is without transactions that are like exactly the same, right? And so, and obviously, yes, it's a log scale, right? So, it's not exactly exponential to 1. But nevertheless, right, if you add a couple of more zeros to the size of the cache, it seems like we can maybe even hit like 99.9% hit rate on our cache, and only run the model on like a 0.1% of the kind of the new transactions that we're seeing. So this is kind of an illustration of this, right? So I specifically focused on entity recognition, right? But this can, be specialized for categories, for like outliers, for different like SQL query generation, right? So instead of like running it through the model, right? Can we actually have a cache where most of the stuff runs through, and then individual for every single task, right? And then only some of the stuff runs through our model. And you can actually really start to push down this kind of plot, right? And maybe actually make human level accuracy accessible, right? Even keeping the model very large. So this is kind of the goal there, right? And these numbers look pretty large, but I think we can even get higher than this. So right. Yes, there are some caveats, of course. This is not exactly, just a key value store you add, right? Exact similarity or not. You need to, first of all, build a specialized cache for every single task. Sometimes there's like changes in the data over time, like some new kind of financial words and conventions, and you have to, like, how do you hydrate parts of the cache, to keep up with that? Sometimes one merchant which was named one thing, changed its name, and then, right? If you have errors in your model, all right, of course, right, and you're gonna write them into the cache, of course, that can propagate, so you need to be sure that the model is really big, right, in some way, of course, if cache is small, you can start to think like, all right, well, this token seems to never change independent of this part of the transaction, but that's only because you have it's so small that the cache has only seen a very small kind of distribution of transactions, and then that can result in mistakes. So, but if we're careful about these things, then actually things look quite promising, right? And so this is kind of the goal we wanted to achieve with this, and then we can build cool shit, right? Using real data, and thanks a lot.
What is some of the cool shit that we can build with this?
Yeah, I mentioned a lot of the stuff in the beginning, right? Like, you can calculate some ESG, like carbon offsets, footprints, right? By looking at, for every payment that you have done, right? Like how much carbon effect does it have? Or you can look at, automating, loans or underwriting, right? Or you can look at onboarding, like cold start problem, right? If somebody logs in with the bank, can we like immediately personalize the app for them, right? And use their banking data to kind of, right? Like, one of our customers actually, they're still in stealth, but they're actually looking into building a dating app on top of of bank transactions, right? So it's like, yeah, like it's you can do a lot of cool things, right? So yeah. Yeah. So exactly. So it is a fuzzy match, but it's a fuzzy match with kind of a very high statistical accuracy, right? So I kind of mentioned a little bit on that, right? So if you have seen, let's say, ACH transactions in the US, for example, right? Like a lot of their patterns is very similar, right? So if you like open a spreadsheet and look at them, it seems like, right, like after INDN, for example, there's always either an org or a person, like independent of the remaining parts of the transaction, right? So then suddenly, if there's another transaction that comes in with also INDN, right, you maybe can just forget about the other entities and just immediately tag that entity, right, and then continue with the rest, right? And if you can, if you have enough stats in the cache that all the entities kind of fall away like this, then you have retrieved it from the cache. But if there's some parts where like you just don't have enough data there's just too much variation, then you run it through the model, right? And then kind of build these stats. So. Yeah. Oh, so money-wise, actually, we haven't. So we have some dedicated GPUs, so we haven't really calculated kind of cost. The time, so for like the 70 billion, or yeah, I mean, that's for Llama 2, but like, yeah, we also have the 65 is about the same ballpark. It's like on the largest, I mean, it really depends on the data. It kind of scales linearly with the data, amount of epochs that you run. It's like an order of like 2 days, something like this, for the largest llamas, and then, and it also depends on the quantization of the weights, right? So actually, like probably the way you want to look at it is the total number of bits in the model, right? Kind of will scale linearly with the training time, right? So, yeah. Yep. Yeah, I mean, so there are several parts to this. So actually, but yes, so the way I guess this could make sense is if, like a lot of these models is actually, they're trained on almost purely synthetic data from like GPT-4, right? With careful prompting. So, but obviously generating a lot of this data is kind of expensive, right? So you can like bootstrap, you can generate a bit of synthetic data to generate a very large model, but still much smaller than the parent one, and then use that to generate much more data for an even smaller model, something like this. We haven't really done much work there, but yeah, obviously that's like a very interesting thing, right? And also like independent of cache or not, right? If your main model can keep the same accuracy, but it's smaller, obviously that's better, right? Yep.
Due to my limited understanding, I'm trying to get an appreciation from a developer standpoint. If you have certain developer skills in one domain, and then you want to enter into the world of deep learning, how much more do you have to learn to go from one area to the next? Or is it, you know how to do, is there a lot of transferability of, if you're pretty much a developer, you're familiar with a few languages, you can pretty much step into the deep learning, experimentation, and creation path pretty easily. I have no idea, so I'm just curious what your perspective on that is.
Yeah, I think like kind of the classic deep learning, right? Whether now it's like kind of building and architecting foundation models from scratch, right, or kind of some specialized models. The main bottleneck there, I think, is kind of just intuition, right? Like for you see like a validation and a training curve, and it's like, all right, okay, this immediately means this, right? And because iterations take a long time, right? And this intuition helps you iterate in the right direction rather than veering off and, So that's more important than even, learning the different functions in PyTorch or something like this, I think. But then if you don't want to do ML, but if you want to do AI, right, obviously that's kind of more accessible now, right? And kind of AI is effectively just kind of using LLMs and prompt engineering and stuff like that. There, I think if you're like an English major and you're really good at succinctly explaining something, then that actually should correlate like pretty well with like prompt engineering, for example. So yeah, it's like I think those two things. Yeah. Yeah. Right. Yes, yes. So this is something we're it's still internal, but might make that public soon. So indeed, right, like your subscription to like Spotify, right, is the category subscription, or is the category like media and entertainment, or is the category, like app store purchase, right? And yes, but the reality is like all of these categories apply, right? So what we really want is our models to return just everything that applies, right? So we can have like a fixed category, or sorry, a fixed hierarchy with all the possible categories, and then it will just pick all the ones from this category which makes sense for each transaction. And that way, returning like a list of categories instead of a single one, you can then on your end decide like which one you want to pick or you want to use all of them. So, yeah.
If we building up the cache, like how much of that is sort of using off-the-shelf libraries or sort of existing technologies that exist versus just building it yourself from scratch?
So all right, so the cache we just use, so for the storage, like we just use Redis, right? Sure, there's faster options probably, like some like local in-memory stuff, but the main part is not actually that. It's like kind of what it's like the .get function from the cache. If when a transaction comes in and you want to get a transaction, or an output that's so. Is there a similar transaction in the cache, or is it not? And if there is, which transaction, right? So that part is like fully custom. Yeah, I mean, that's just algorithms, right? Similarity functions. Also different bucketing of different parts of a transaction, looking at stats, mostly Python, really.
How are you, in terms of those, I guess, key management and notes, then, are you doing that as vectors, or are you doing that as sort of puzzle keys, or how are you?
We're running a few experiments on that. Actually, currently not even using so much vectors because like an embedding model, that's like a little bit of another can of worms, right? Because obviously transaction data is not really text, and if these models are trained on original text, something which looks similar might be actually very different, right? So we're trying to like avoid embeddings as much as possible for this, because as soon as you introduce some like, like a 1,000 parameter vector, you immediately hit accuracy, right? So, or right, you can, I mean, yeah. It might be that in the future, actually, like we're add-on embeddings, and then there's a lever you can tune between hit rate and accuracy trade-off. To be honest, like the cache stuff it's like very recent. Yeah, it's just really the last months. So we're in exploration mode there. Mhm. So bandwidth, you mean like throughput, like how many transactions? I mean, throughput, you just add more GPUs, right? It's kind of, if you can get an allocation, which is like pretty hard now, right? It's like, yeah, at least on like the A100s and H100s. But so throughput, yeah, like throughput. Okay, so obviously there is, if you're using like directly like ChatGPT or something like this, right? They have quite a low rate limit, right? Like 200 requests per minute or something like this. Yeah, I know some people, they're just creating different orgs with different API keys and randomly picking a key from those, but that's a little bit of kind of hacking, right? Azure also has a deployment of GPT-4 models. You can use the Azure key, but that's the same rate limits there also. But at least they can double your throughput for that. I mean, yeah. Still want to go to cache? Yeah, I mean, cache is cheap, right? Like the retrieval time is just a few milliseconds. So you can do. So it's kind of it's specialized for every task, right? But then but it's not specialized for the distribution of transactions, right? Like a machine learning model is specialized for a task and it's specialized for a distribution, right? If you get an out of distribution transaction, right, like from a different region of the world or something like this, and you feed it into the model, and it's like really far outside, you're probably going to get very low accuracy. But with cache, it will simply just call the model instead because there's just not enough stats there. And then we'll automatically start building a bucket for that distribution of transactions, right? And this distribution could also be a different language and stuff like that. So it's kind of automated, semi-automated for distribution drift, but you still need task specialization. Yeah, that's maybe also like in the future, since this is quite like like an early version of the cache, we'll manage to like abstract it across multiple tasks, but let's see. Yeah. Cool. All right, well, thank you.